Okay, so the problem we're going to be looking at is the exploration of the solution to Laplace's equations in cylindrical coordinates in order to find the potential, free and bound charge, and the electric field inside of a grounded cylinder, shown over here, with radius A, height h, and one end cap held at potential negative v1, and with a little added bonus of having the bottom half up to half the height filled with water, liquid water. In order to solve Laplace's equation, we're going to need to know the boundary conditions, and the ones that we know and are particularly relevant to our solution to this are that we know that at height of 0, or z of 0, the potential is 0. At the edges of the cylinder, where our radius is a, our potential is 0, and at the top of the cylinder, where our height is h, the potential is negative v1. We can then solve Laplace's equation in cylindrical coordinates, which you can see here. However, we know that this term goes to 0 because our solution should theoretically be phi independent, as our potential should not depend on where we are, meaning that we have isothermal symmetry, I believe. Going over the next couple steps, we can assume that the solution is in the form of the product of two independent functions, both the first of a function of s, the second as a function of z. We then find Laplace's equation for that, and we rearrange such that all of our functions of s are in one part and the functions of z are in another, in this case by dividing out r of s and z of z, coming to this form and this form. We then split those up into two ordinary differential equations. So we say, okay, if they overall add to 0, we know that one must be the opposite of the other, equal and opposite to the other. So we set some arbitrary constant k, and we say, okay, this function is equal to the opposite of this function. And then we say that they both overall have to be 0. We move k across, so it's both solved for 0. And then we can solve these now ordinary differential equations for r sub s and z of z, or r of s and z of z. Starting with the easier of the two, z of z is in the form of an exponential. Looking at it here, we can then say, okay, it's a pretty safe guess to say that a e to the kz plus b e to the negative kz could be a form of z of z. And then we can solve for a and b by using our first boundary, or our third boundary condition, where our potential at height of 0 should be 0. We can say, okay, we're going to plug in 0 for z, our height is 0, and then we know that the potential is 0, so overall this function must be equal to 0. And that allows us to solve for, okay, a plus b is 0, a must be the opposite of b. We can then plug that back in. We know that z is now a e to the kz minus a e to the negative kz, and that conveniently is exactly the form of a sine h, or the exponential sign of kz. Okay, we found the z portion of our potential function. Now we need to find the s portion. We can split up our s portion by kind of splitting up our r of s here and our r of s here, and we get this form here. And it just so happens that this function that we're looking at here is actually something known as a differential function with a solution in the form of something known as a Bessel function, or solution is a differential. This differential equation is of the form of a Bessel's differential equation, which means that a solution of this equation is a Bessel function, which you can denote as either j sub alpha or y sub alpha. And you would rewrite this to say that the r function that we have, this r of s, that describes the radial portion of our potential function, is now written as a Bessel function, j naught of kz.
Bessel functions were first formulated by Daniel Bernoulli and later generalized by Friedrich Bessel as solutions to Bessel's equation, which is shown here. Here, alpha is a constant, and it can be any complex number, and it denotes the order of the function. Here, we're only going to care about the positive integer versions of alpha. So, since Bessel's equation is a second order differential equation, we expect there to be two independent solutions, known as the first and second kind. The first kind, denoted as j sub alpha, are defined here for the integer coefficients as being this large sum. And you notice that in the bottom there is a gamma. That gamma represents the gamma function, which is a generalization of the factorial to all real numbers except for negative integers. This is just kind of showing all the possible ways you could do alpha. There's also contour integrals, which we're not going to care about. And here, this is really the only place where you should really note this function. Here we see a plot of the first five orders, so all the way from J0 all the way up to J4. Note here that the only order that is non-zero when starting at 0 is the 0th order. This is important. It's going to be important later on, so keep note of that. So the second kind of Basel functions are much more complicated. For example, this is just the definition for the 0th order second kind. If we instead look at for integers greater than 0, then we get this very, very messy function. However, we know we don't have to care about this because if we look at the graph of all of these functions, we see that there's a singularity at 0, and then they all kind of converge around the y equals 0 line later on. So once again, going back, this is the function for the second order. You don't have to care about it. If you do, these are some of the coefficients that are defined in it. But once again, this isn't going to be important through our thing. So the reason why I wanted you to keep notes of how the first order Bessel function acted was that we know there must be non-zero potential at a equals 0 through that center line. So that's why we can know that we only really have the 0th order as our solution to our equation here. And specifically, we also know that at the edges of the cylinder, when s equals a, that the potential must be equal to 0. This is one of our boundary conditions. This tells us that k of a must be one of the roots of the Bessel function. So, going back to the graph, you notice how the functions oscillate up and around the y equals 0 line. All of those are going to be the roots of the Bessel function, of which there's an infinite number. So we say that k of a is a root of the Bessel function, and we can use this to help later solve on. But we have to make note that because there's infinite of these 0 roots, which we'll denote as b sub n, that there are also an infinite number of solutions for just r of s, which is fine because we expect there to be infinite solutions to Laplace's equation anyways.
And then we can plug that into our original overall potential function with both our z component and our r component to get that our overall potential function is the sum from 0 to infinity, from n equals 0 to infinity, of a sub n, 0th order Bessel function of k sub n, sine h of k sub n times z. Now we have to solve for the constant a sub n using the first boundary condition, which was, as just as a refresher, that the top cap of the cylinder must be kept at a constant potential negative v1. So at z equals h, the potential must be negative v1. And in order to solve for this here, we actually use a Fourier trick, but specifically one using Bessel functions. We will actually ask you to prove this in the homework problem. Prove that this down here, these two are orthogonal to one another. But for now, we'll say that this Bessel function of k sub ns is orthogonal to this Bessel function of k sub ms. Essentially saying that they have distinct roots, but will equal 0 everywhere that m is not equal to n. So you'll get this delta function where it is only non-zero when n is equal to m. And we can then use that Fourier trick to take the integral of both sides, multiply by the Bessel function of k sub ms, and then take the integral of both sides from 0 to a with respect to s. And then we'll find that because of the normality condition, this over here, portion here, is equal to the integral of this. We'll then find the integral of this portion of the function, which using properties of Bessel functions we'll find to be these constants multiplied by now the first order Bessel function of k sub n a. We'll then get this form of the equation. And now in order to solve this integral, we'll actually use a really cool trick, really clever trick, where we take the original differential equation that was defining the potential from Laplace's equation. We multiply specifically the r of s component of that equation by 2r of s times s, and we let a equal 1. So you'll see that here. You multiply this in black is the original portion of Laplace's equation with respect to s, and we multiply both components by 2r of s times s. And we find that now we have this here and this here, the derivative with respect to s of this inside this, and then 2 times k sub n squared s squared r sub n of s r sub n times s is equal to 0. We take the integral of both sides, and we'll find that this from 0 to 1 is just a r sub n s squared. This actually entirely goes to 0 because at 0, s is 0, so this function goes to 0. And at a, r sub n is 0 because we defined a as a root of r sub n, right? So r sub n at a is equal to 0. So at both of these at 0, this entire term goes to 0. And then this derivative here, we don't actually have to take this derivative because this is exactly what we're looking for when we're trying to solve this back here. S times our we'll convert to the Bessel function. We then solve the left side of this function, a r sub n s squared to equal all of this what you see over here, and for the general case that r of s is equal to our Bessel function, Bessel function sub 0 of a k sub n, and you simply imply a u substitution for where u is equal to a k sub n. You then solve the right side using the property here of Bessel functions, where the integral of your variable to the power of v, to the power of u, the Bessel function to the case u minus 1 of your variable, d your variable, is equal to the variable to the power of v to the power of u, Bessel function of an order of u of the variable plus c. You use a u substitution, as we described previously, where u is equal to k sub ns, and then you find that this integral here is actually equal to this over here, which you can eventually simplify out to negative v1 over k sub n, a j sub 1 b sub n. You can then find the coefficient a sub n by making it so that your a sub n here, here, is whatever it needs to be here. Your a sub n here is whatever it needs to be such that the it cancels out all of these things, all of the j sub 1, first order Bessel functions, a squareds and k sub n squareds, in order to make the left-hand portion of the function equal to the right-hand portion of the function. So a sub n has to be this. We can then plug that back in, and we'll find that our overall potential function now looks like this once we've put a sub n back in, and where b sub n is k sub n a. We can then find the electric field by taking the negative gradient of the potential, and also we'll have to use some identities of the Bessel functions with respect to the derivatives of the Bessel functions, such as the ones you see here, as well as the derivatives of the exponential cosine and sine. You can then solve for the electric field, which you can see written here once you've taken those derivatives, which has both an s component and a z component. And then in order to solve for the bound charge and the free charge, we know that in a homogeneous isotropic linear dielectric, the bound charge is proportional to the free charge. And we know that the free charge is equal to 0 because it's grounded. And we know that the uh, permittivity above times the potential above in the direction of n minus the permittivity below times the potential below in the direction of n is equal to the negative charge distribution, free charge distribution. We know that the permittivity above is permittivity of air, permittivity below is a permittivity of water, which we'll call epsilon sub r. And then we can solve for the bottom end cap, where our n hat is negative z, pointing out of the cylinder in the negative z direction. You'll find that the free charge is this here. The free charge distribution is this here. And on top of the water, so at h is the height is h over 2, or z is h over 2. Z is now, the n hat is now pointing in the positive z direction, so we'll find that the free charge is what you see here. And then on the sides of the water, our n hat is now pointing out of the cylinder in all directions in the s hat direction, so in the direction of the radius. Our free charge distribution looks like this. We know the bound charge total has to be 0, and we know that the bound charge distribution is equal to the polarization times that area unit vector n hat. And we know the polarization is equal to the permittivity times chi times the electric field. And we know that on the bottom for the bound charge, once again, z is positive z. And we find that the bound charge distribution is what you see right here. And on the top of the water, once again, n hat is equal to positive z hat. Bound charge distribution now at z equals h over 2 is what you see here. And on the sides of the water, where n hat is equal to positive s hat out of the cylinder in the radial direction, the bound charge is this sum right here. Thank you so much. These are our references.